The remainder of this chapter in the textbook talks about electric fields and does some derivation of equations describing electric fields for various charge configurations. In fact, that's the remainder of the chapter, deriving electric field equations for various charge distributions. So let's begin by taking a plate, a metal plate, conducting plate, but there is charge on this confined to one side. Let's say we have positive charge on this side here. And let's say some distance away, a relatively short distance away, there is negative charge, an equal amount of negative charge. So if this is plus Q on that plate, there is minus Q on that plate. Now, these are parallel plates, so this would be like something like this, and we're looking at it edge on that way. So they have some surface area that goes into the sheet of paper here, into the plane. And we're looking at these edge on. Now, we've talked about fringing and how fringing would occur near the edges, but here in the central region, there's going to be electric field lines that point down like that. And as long as we don't get too close to the edge, that's going to be a constant and uniform electric field in that region right there. Well, let's say we take another charge. We'll put a charge right there, and we'll call that charge Q naught. Now, Q naught has forces acting on it. Now, Q naught is certainly going to have some electric force acting on it because it's in the presence of an electric field. But it also, in this case, has gravity pulling down on it. And we can't ignore gravity in this case. So if we draw a free body diagram, this is the body, Q naught. And there's a downward force due to gravity. That's just its weight, mg. And then there is an electric force due to F, if this is a negative charge. Okay, so if we have a negative charge right there, it's going to be going upwards in that direction. If this had been a positive charge, we could have reversed the polarity of these two plates, and that force would have still been upward in that direction. Okay, well, if that charge is suspended there, held with no net force on it in between the two plates, so it's just suspended there, then those two forces are in balance. So F, which is the electrostatic force, and we can write that as the electric field times Q naught. That comes about from the definition of what electric field is, and that's equal to mg. So if we want to determine what the magnitude of the electric field between these two plates that will levitate a charge, Q naught, between the two plates, then the magnitude of that electric field is just mg over Q naught. And the direction is going to be downward if Q naught is negative. The direction of the electric field would be upward if Q naught were positive. But that's the magnitude of the electric field right there. So when I say the rest of the chapter derives equations for electric fields based upon various charge distributions, this is an example of that. This is a pretty straightforward example of charge that exists on two parallel plates. Now, this will pop up later on when we start talking about capacitors. So this type of system where I have positive charge on one plate, negative charge on another plate, parallel plates, and with electric field in between, a continuous constant electric field in between, that's called a capacitor. And we will encounter capacitors later on when we get to the section on capacitance. Let's talk about the electric field due to a dipole. So let's say we have a dipole. A dipole is a point charge, let's say plus and minus, and these two charges are the same, so we have plus Q there, minus Q there, so they have the same magnitude and opposite polarities, and they're separated by some distance, and we can call that distance of separation from there to there, we'll call that D. Now there's the center of the separation. That would be the center of the dipole. And let's say that we want to measure the electric field at some point out here. Let's pick a nice easy point, let's say along this dipolar axis. So straight up along the dipolar axis, way out here somewhere, at a point like right there, we want to know what is the electric field at that point, okay? Well, this distance then from, let's say from the center here to the point itself, that distance there, let's call that distance z. Now we're going to make an assumption here. We're going to assume that d, this distance between the portions of the dipole, is much, much less than z. So if we were dealing with a real dipole, then d is going to be on the order of nanometers. Z is going to be on the order of centimeters to meters. So this is a macroscopic measurement. This is a micro or nanoscopic measurement. Now let's think about the electric field at this point due to these two charges that are some distance away. The positive charge in this case is always going to be closer than the negative charge. So if I drew the electric field due to the positive charge, it's going to point in that direction along this axis here. So let's call that E plus. And then I'm going to have electric field in the opposite direction for E minus. Now those two are not equal in magnitude. The E plus in this case is going to be a little bit larger than the E minus. So if I wanted to know what is the total electric field, it's just going to be E plus minus E minus. Now I could write that way, but if I were going to use real vector notation, then I would make that a plus. That makes it more generic, and the negative sign would be associated with this, with the vector itself. So we would have a negative sign there. However, nevertheless, in this case, if I was only interested in the magnitude of the electric field, because I know the direction. If E plus is larger than E minus, then the direction of the net electric field is going to be upward along this axis pointing upward like that. But if I'm only interested in the magnitude, then it's going to be the magnitude of E plus minus the magnitude of E minus. Now magnitudes are always positive quantities, so that's why the negative sign is necessary here. All right, well, let's use Coulombs Law. This is K, Q, over the distance to the positive charge. Now, we need to work here. The distance to the positive charge from that point is going to be Z minus D over 2. So from that point there to that point there, that distance there, that is Z minus 1/2 D. And then to the negative charge down here, that distance to that point, this distance here, that's going to be Z plus D over 2. So right here, what needs to go here is the distance to the positive charge from that point. So that's going to be Z minus D over 2 quantity squared minus K Q over Z plus D over 2 quantity squared. So that's the electric field for those two, E plus and E minus. That's the magnitudes. Now you can see that we have some things in common, so we can factor some things out. Let's factor out a K and a Q. And then I've got 1 over Z minus D over 2 squared minus 1 over Z plus D over 2 squared. There. Okay. Now, if we had numeric values for this problem, here's what you would discover. Since we made the assumption that D is much, much smaller than Z, then what that means is that this quantity down here, since Z is large compared to D, and I'm dividing D by 2, then Z minus that very small number and Z plus that very small number are almost identical. So these these denominators that are on bottom here are going to be almost exactly the same. Now, if, like I said, if the assumption is that this is on the nanoscale and this is on the macro scale, then you're probably not going to have enough enough decimal points in your calculator in order to display this once we do 1 over and the squared. So if you had nanometers for this, you could even do this with your calculator. Do nanometers for this and do, let's just say 1 meter for that, and then plug it in. You're just estimating numbers, plug it in, and do this calculation that's in the square brackets there. And you'll see that it's effectively 0. So we need better resolution if we want to do this. And there is a way to achieve that better resolution. We can make some approximations. And what we can do is we can use the binomial theorem. The binomial theorem you may have encountered and probably have encountered at some point in your mathematics career. And it says this, that if I have 1 plus or minus some x value raised to the negative n, then that is actually equal to a series. And that series is a never-ending series, but each term of the series gets smaller and smaller and smaller and smaller. So you could take this series out to ever how many terms you care and get the approximation that you need. So that series looks like this. 1 minus or plus n x over 1 factorial plus n times n minus 1 x squared over 2 factorial plus, and that series just continues on. That same trend continues on. And this is for cases in which x squared is less than 1. So what we need to do is we need to put e, this equation for e, the magnitude of e, into this format so that we can use the binomial theorem and apply the binomial theorem to it. So let me show you how to do that. We'll start right here and just rewrite kq over z squared times, all I'm doing is factoring out a z squared from the bottom. And if I factor out a z squared from the bottom, I have to multiply it on top. So this is going to be z squared over z minus d over 2 squared minus z squared over z plus d over 2 quantity squared. Okay, now I have terms that are in here that I could factor out that squared term and just say the whole thing is squared. The whole thing is squared. But I'm going to do that. I'm going to do that the next step. But I'm also going to take the reciprocal of that and raise it to the negative 2 power. So I'm going to rewrite this as kq over z squared times z minus d over 2 over z, and now raise that to the minus 2. That's a 2. My z's and 2's look the same. That's the reason I cross my z's. Minus z plus d over 2 divided by z. Raise that to the negative 2 as well. And there, now I have something that I can distribute this, and it will look like my binomial theorem over here. Because look, z over z, that comes out to be 1 minus d over 2z, that's the x. And over here, the same thing, z plus d over 2z. So let's take another sheet and let's distribute that out. So now E, we're taking this right here, and we're going to rewrite that as kq over z squared times 1 minus d over 2z raised to the negative 2 minus 1 plus d over 2z to the negative 2. There. Okay, now we can apply the binomial theorem to each of those terms. Remember, reminding you, binomial theorem is this: 1 plus or minus x, and in our case, x is this term right here. And it's raised to the negative n, so n in our case is 2. All right, so let's apply the binomial theorem to this, and we're going to end up, now we don't have to do a lot of terms. In fact, we're just going to do the number of terms that I have here. There could be a third, fourth, fifth, or infinite number of terms. Each one increases the resolution of your calculation as you go through that. But there's no need for us to do that. We're just going to keep the first couple of terms. Actually, the first 3 terms, because the first term is a 1. So we're going to have k q over z squared multiplied by, now this is 1 minus x to the negative 2. So I'm going to write that as 1 plus, remember, if this is plus minus, then this is minus plus. All right, and we have a negative sign here, so we'll have a plus sign here. And this is going to be n, which is 2, times x, and x is d over 2z, divided by 1 factorial, which is just 1. So that's this first term. Right there, we've written down the first term. Now, the next is just plus. Plus n times n minus 1 times x squared over 2 factorial. So the n is 2 times n minus 1, which is just 1, multiplied by x squared, and x is d over 2z squared, divided by 2 factorial, which is 2, plus, and dot, dot, dot. And that takes care of this first term right here. Now, let's do the second term. Minus, and we're going to have another set of parentheses here. Minus, because I'm putting things in square brackets here. Let's do this term and expand it. That's going to be 1. And since now we're dealing with a positive sign here means that we need the negative sign there. Minus 2d over 2z plus 2 times d over 2z squared divided by 2 factorial, which is 2, plus dot, 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 dot. There, and close the brackets like that. Okay, so here we have our expansion of these 2 terms so that we can try and get better resolution. Well, you'll notice that some of these things are going to cancel. First of all, the 1's are going to cancel each other. The 1's are going to go away. So that and that cancel each other. The next term, the 2d over 2z, those don't cancel each other because this negative sign is going to make that a positive, so there's going to be 2 of those terms. And then this next term, the 2 over 2d 2z squared, is going to cancel. So this term and that term are going to cancel. So out to this third term here, you're really only dealing with that 1 term. So this can be rewritten as k q over z squared times, and now there's going to be 2 of these, so there's going to be 2d over 2z terms, which means that when I add them together, they're going to be 4d over 2, and whenever I cancel, so it's just going to be 2d over z, like that. All right, at this stage, I just want to rearrange the terms here. I've got K, Q, D. Let's put the 2 over Z cubed out here. Now I want to take this K. Remember what K originally is. K is 1 over 4 pi epsilon naught. And let's move the 2 out here. And now I've got Q D over Z cubed there. Well, let's go ahead and simplify this. This is going to be equal to 1 over 2 pi epsilon naught Q D over Z cubed. And that is the magnitude of the electric field at our point, some distance Z away from the center of a dipolar molecule, with the assumption that this molecule, the distance between the positive and negative charges, is very small compared to the distance away. And that will be the case if we're dealing with something like a water molecule or any other dipolar molecule. Okay, now there's the electric field equation. This quantity here, Q times D, that is a quantity that has been defined and utilized because it turns out if you had to measure these in the laboratory, if you had to measure Q and D separately, it's a little more difficult to measure each independently. Instead, to measure the product of those two is a little easier. That's called the electric dipole moment. Okay, what is the electric dipole moment? The variable that describes it is P, and it is equal to Q times D. Now, it turns out that P is a vector, so its magnitude is just Q times D. And it has a direction, and the direction is like this. So if this is the positive, that's the plus Q, and here's the minus Q that makes up the molecule, then P always points from the negative to the positive. So that's the direction of P, always from the negative to the positive of the dipole. Now, if we introduce this, and this is a very common term, and this term is going to pop up quite a bit as we go through the rest of the course. The electric dipole moment, P is equal to Q times D, is right here. So this can be written as 1 over 2 pi epsilon naught times P over Z cubed. Once again, that's the magnitude of the electric field. But we can make this now into a vector equation if you recognize that with this direction here, for our example up here, it's going to point upward. So we just turn that into the vector, turn that into the vector, and now we've got a vector equation that describes the electric field, both magnitude and direction, in terms of that vector P. So there is the electric field due to a dipole along, and this only works in our special case here, along this dipolar axis. Okay, so there are a couple of things I want you to notice here. First of all, notice that this is a 1 over Z cubed relationship, and this is for a dipole. When we were dealing with point charges, and there was just a single point charge, the electric field was proportional to 1 over the distance squared. So 1 over the distance squared. And that was a single point charge, which is called a monopole. So a monopole is 1 charge. A dipole is 2 charges. And you'll notice there's a trend here. Even though we just have 2, you can spot it easily. This is a 1 over Z squared. This is a 1 over Z cubed. There is such a thing as a tripole. And there is such a thing as a quadrupole. So the tripole is going to be 1 over Z to the 4th. And the quadrupole is going to be 1 over Z to the 5th. So that trend continues as you get more and more charges to make up these weird configurations of molecules, that the electric field changes like this. So the electric field for a dipole falls off a lot quicker as an inverse cube compared to an inverse square. And now at great distances then, as z becomes very large compared to d, then this very quickly goes to 0 because of the distance, because it's 1 over the distance cubed. Whereas for a single point charge, it would fall off slower, more slowly, as 1 over inverse squared, or inverse squared, 1 over r squared, distance squared. So a dipole is going to appear to be no charge more quickly than would a monopole, for example. Okay. Something else I want you to notice is, let's take our dipole here. There's our dipole. And let's say now that we wanted to know what is the electric field some distance out here, where this is now a right angle. So some distance r out here. Well, the electric field due to the positive charge is going to point that direction. The electric field due to the negative charge is going to point, that's going to be more towards the negative. I should have drawn that a little more carefully, but this will be E minus pointing towards the negative. This will be E plus pointing away from the positive. And you'll see the net electric field in this case is going to be downward like that. Okay, so will this equation work? I believe, as if it's not a homework problem, then it is a problem that you could work. What is the electric field magnitude for this situation here? You could figure that out pretty easily, I think. You could write an equation for the electric field using the same sort of reasoning that we did here, maybe even easier. So far, everything we've done has been for point charges. So we've had a single point charge, we've had dipole. Let's talk about a continuous charge distribution and see how you would work that type of problem. So let's start with the simplest case. Let's start with a line of continuous charge. So let's say that we've got a line here, and this line has some positive charge on it. Now this is no longer a surface seen from the edge. This is a continuous line of charge. We could even say that it has some known length, L. And what I want to know is at this point right here, straight off. So normal coming off at a 90-degree angle from the line at a point in space, which is right there. And that distance is, let's say, big R away. Okay, now this is a continuous charge distribution. So we would have some known value, and we have a constant, lambda. Remember what lambda is. Lambda is the linear charge distribution. So this is charge per length. And the unit for that is going to be charge, which is coulombs per meter. So lambda is the amount of charge per length that you have for this continuous charge distribution. And the unit's going to be charge per meters. And it's going to be a constant. So it has this, you can think of this as a linear charge density or linear charge distribution. Now what we want to do is we want to figure out the electric field at that point right there. So we need, in order to do this, we need to figure out both magnitude and direction for the electric field. Well, we really don't know how to do this. We know how to solve for the electric field due to a point charge. And remember, for a point charge, the electric field E is just KQ over R squared. Well, we can use that bit of information here if we can treat this like it's a point charge. But since it's a continuous charge distribution, we can't do that really unless we are just talking about a tiny portion let's say a small little bit, that portion of the charge that is in this region right here. Now we can make that as small as we want, but that is a tiny little portion of the total charge distribution. It's so small that we can treat it like it's a point charge. So we'll say the amount of charge in there is some differential value dq. And it is so small that we can treat it as if it is a point charge. And that is a distance away from here, and we call that little r. Big R is the fixed value. Little r, though, could change, because I think you can see what we're going to have to do. We're going to have to integrate along this whole length here. The equation that we get for that point charge, we're going to have to use the whole length and do the integral of that equation. Okay, so we need some more knowledge here. Let's say the distance here to that point charge is x. We'll call it the variable x, and of course x can vary. X could go from 0 to, let's say, plus L over 2, or 0 to minus L over 2, back in that direction. Or we could say from minus L over 2 to plus L over 2. And the amount of charge in that little section right there, we'll have to give that section a length, so we'll just call that the differential length dx. So dq is the amount of charge that's in dx length. But that charge is a distance x away from this center point here where r comes off. All right, you see how it's working? Lambda is constant. So lambda, if I wanted to know what, if I knew what the total charge was, q, and I knew what the total length was, L, then that's what lambda is. Lambda is just going to be big Q over big L, like that. In fact, let's say that we do know what the total charge is here. Since we have a fixed length, we are going to have a fixed value of charge, and let's just say that's big Q. So big Q is the total charge. Little q, that's the amount of charge in dx, which is a distance x away. All right. Now, in order to work this problem, we need to be able to create an equation for the electric field. Well, the electric field, due to that differential piece of charge there, since this is positive, is going to be in that direction. So that is dE, like that. Now, as we integrate this, you can just imagine that dE is going to point that way, and then it's going to point that way as we integrate to the left-hand portion. So we need to be able to break up dE into component parts. And the easiest way to do that is to break it up into a vector that goes that way and a vector that goes that way. And in order to do this, we need an angle. So let's call this angle right here theta. And theta is going to change as we integrate this. So theta is actually a variable. It's the angle from 0 here. This is the 0 point to x. All right, now if that's the angle theta there, then this is the angle theta here. So that makes this component here the dE cosine theta component, and that makes this the dE sine of theta component. Okay, that means for each of these two components we would have to do the integral twice, once for the cosine term and once for the sine term. But if you look at the symmetry here, you're going to discover that one of these components cancels. And just think of it this way. If there is a component down here, x distance away, that has the differential charge dq in it, then x distance away down here, there's going to be another differential charge at this point, and the electric field for that is going to point in this direction. Let me see if I can draw that using a slightly different color here. So there's going to be a dE that points in that direction, and that dE could be broken up into a component going this way and a component going that way. And you can see what's going to happen. These terms there, the sine term and this sine term, are going to cancel each other. So the net effect of doing this integral all the way across is that the cosine terms are going to be the ones that add together. The sine terms are just going to cancel each other. So rather than doing the integral twice, once for the sine component and once for the cosine component, we really just need to do it once, and that's for the cosine term. Everything else is just going to fall apart. So if E is equal to kq over r squared, then this differential electric field caused by dq is going to be given as dE is equal to k dq divided by the distance it is away from that point, and that distance we've called r squared. R is a variable. Okay. So that's the dE, but we need just the cosine portion of that. So this is, to get dE cosine theta, it's going to be this, k dq over r squared, times the cosine of theta. And the cosine, if you'll think about what the cosine is adjacent over hypotenuse. So it's going to be big R over little r. Here's the angle theta. This is the adjacent side. And this is the hypotenuse. So this term here is the cosine theta. And what is that? Well, we can change that to k dq big R over r to the third, like that. Okay, now r itself is a variable, and we need to be able to integrate this. Whenever we integrate over all the dE cosine theta terms, that's going to give us the total electric field. So this is the dE cosine theta. So this is what we need to integrate right here. But we need to figure out a way to do that. Okay, right now we've got dq there, we've got r there, that's a variable. So we need to figure out a way to make this so it's something that we can integrate. The easiest thing to do is to recognize what we have here is this triangle. So we've got that is x, this is big R, that's theta, and this is little r, like that. So little r is the square root of x squared plus big R squared. Now big R is a constant, so that's not a variable. However, the x is a variable. What we're doing in this case is we're changing the variable here from r to x by doing that right there. So if I have and we'll just rewrite that to the 1/2, that's what r is, then r cubed is going to be x squared plus r squared to the 3/2. All right, so let's plug that in here. We're integrating k. Now dq, let's think about dq for a minute as well. And we need to use this bit of information right here. If we were talking about just the differential dq, then lambda, which is a constant, remember, is equal to q, in this case it's just dq, that's the amount of charge in this distance dx, divided by the length dx. So if I want to know what dq is lambda dx. So lambda dx times big R over x squared plus r squared to the 3/2 power. All right, now that looks more like something we can integrate, and the limits of our integration are going to be from minus L over 2 to plus L over 2. Now we've got some things here that we can factor out, so let's factor out what we can. This is K. Lambda is a constant. Big R is a constant. And everything else from minus L over 2 to L over 2 of dx over x squared plus r squared to the 3/2. That's a 3/2. This is something that I don't expect you to be able to integrate in class. This is the kind of thing that you go to an integral table and look up. And if you were in a math class, you would be required to integrate that. This is not a math class, so don't worry about that. And this integral here, I won't give you anything that difficult on an exam, so don't worry about it. But for the purposes of this example, let me tell you what the answer is. This is going to be K, lambda, big R. And then when we integrate this, it's going to be 2 times 1 over r squared x over square root x squared plus r squared. Now, I did something tricky here. I put a 2 because of the limits here. Whatever we do on the right-hand side is going to be duplicated on the left-hand side. So that I added that 2 there, and now I'll change the limits. Rather than going from minus L over 2 to L over 2, we'll just go from 0 to plus L over 2. Okay, and that's allowed because this would be an even function. Whatever we get going to the right-hand side, we're going to get the same thing going to the left-hand side. So we'll just do the integral from 0 to L over 2 and multiply the findings by 2. That's where that came from. Okay, when you plug in the values, and you can do this if you want, I'm skipping a lot of steps here. Here's what you end up with. The electric field is equal to K lambda L over R square root of L squared over 4 plus R squared. That is the value for the electric field a distance r away from a continuous charge distribution. Okay, now we could rewrite this in terms of the total charge Q. Remember I said we could say that total charge Q is a known value because lambda times L is Q. So if you wanted to rewrite this, you could write this as K Q over R square root of L over 2 squared plus R squared. There. Just another form to write it down. And what about direction? Direction is going to be downward as drawn. And let me caution you, if you're answering this on an exam, the as drawn part here is very important. Otherwise, I don't know what downward means. So the electric field, net electric field, is going to be downward like that, at that point. Okay. Now, let's take that. I'll transfer it to another sheet. The electric field is K big Q over R square root L over 2 squared plus R squared. There's the electric field. You can check this, at least do a mental check on it, by imagining what's going to happen if R, big R, gets really, really big. I mean, if big R gets really large compared to L especially, then what's going to happen? Well, that's the same thing as saying that the L term goes to 0, okay? Or the R term gets very large. So look at this. If the L term goes to 0, then this term right here goes away. So I'm imagining in the limit as L goes to 0. What happens is this becomes R times R, and what that becomes as L approaches 0, E approaches KQ over R squared. And that should make sense to you because this is the equation for the electric field due to a point charge. If that point charge was Q and you were a distance R away, then this is the value of the magnitude of the electric field. And that's what would happen if R becomes very, very large and the apparent size of this charge distribution gets smaller and smaller so that L is effectively 0 as you get really far away from it, then all of this looks like a point charge. And you would expect the electric field equation then, what was here, to reduce down to a point charge, and it does. So you can see there, that's at least a mental check on whether or not you did the exercise correctly. Okay, let's move on and do something else. Let's say I have a charge distribution that is continuous, but it is in the shape of an arc. So there's an arc. So that's an arc of a circle. If I were to continue that on around, it should be a nice circular drawing, a circle. Let's say this distance here is R. And if that's the center of the circular arc, then this distance here is also R. And let's say that we've got an arc here that has an angle of 120 degrees. Okay, and what do I want to know? I want to know what is the E at that point right there. All right, well, if, let's say, what kind of charge do we have here? It's going to be a negative charge that is continuous. So we have a continuous charge distribution. What we need to do is we need to figure out an equation for some small differential portion here. Let's say this little charge segment right there, that can be our dq between those two lines there. That's going to create an electric field that points in that direction. So let's say that's our dE. Well, dE points that way. If I can figure out an equation for dE and then integrate over this arc of 120 degrees, then I can figure out what the electric field there is for the entire arc. Now, my line is short of the edge, but we'll just assume that we're interested in the portion that's in here that's 120 degrees and nothing else out here beyond exists. Okay, so I think you can see what we need to do here. We need to figure out an equation for dE and then do the integration. Well, let's see, what is known in this case? Well, let's say the total charge is known. That would be big Q. So there's a total amount of charge of big Q there. This distance R is also a known value. And that angle theta is also known. That's a fixed value of 120 degrees. It's not going to change. All right, well, we need to do a little bit of algebra here in order to figure out what dE is going to look like. But I want to remind you of something. Remember this relationship, S equals R theta. Now, this R and this theta are not the same necessarily here. This is from algebra. This is an arc length. This is a radius. And this is the angle. So if I had an arc length that much, and I had this angle theta right here, and that distance was R, then this is the arc length. The length along that angle is S. So you may have seen this equation somewhere in your algebra career. I just want to remind you of it. Now, this equation really only works if theta is in units of radians. If you start plugging in degrees for theta, it's not going to work. It only works for radians. Now, if that's S equals r d theta, in our example here, r is a fixed value. And if we were to integrate over this length, then remember, this theta is not that theta. We're integrating over that length, that theta. Then, and that this theta up here is the total 120 degrees, but we're doing an integral over that theta starting from 0 to 120 degrees. Then I can take the differential of this, and that's just ds, is equal to r. R is going to be a constant in our case, times d theta. Okay, that is going to be helpful to us a little later on. So if, just to show you what we're talking about here, if here's our arc length, and this is the section ds, and within that section there is dq amount of charge right there, then from one side of that to the other side of that, that angle right there, that's d theta. Okay, the r value is fixed. Okay. All right, let's draw a free body diagram now. So we've got our arc here. Here's our center, and let's pick a segment out here, which we will call ds. That's the arc length inside our segment. And within that, there is charge dq. Now it's negative, so that creates an electric field that points in that direction, and that electric field is dE. Now, dE can be divided up into segments, one going that way, into components, one going that way, and one going that way. This distance from there up to there, that's a fixed distance of r, little r. All right, well, in order for us to do this, we have to have an angle. We need an angle so that we can break this up into components. And this angle right here is probably the easiest one. We'll have a dE cosine of that angle and a dE sine of that angle. Now, once again, if you'll think about the symmetry of this situation, for a component up here, there's going to be another component down here. That's going to create an electric field in that direction. And if you break this one up into components, you're going to have that and that. So what's going to happen is these sine components are going to cancel. And the sine components go away. So the dE sine theta components, they cancel. And that leaves the dE cosine theta components. And this theta here is the variable that's going to have to cover this entire arc length of 120 degrees. So theta, depending upon how we integrate it, is going to have to go from, 60 degrees to negative 60 degrees, or what is that, pi over 3 to negative pi over 3. All right, so our dE itself is k dq over r squared. Total charge q, then we get if we were to integrate all of the individual dq's, and that's just the integral of lambda over all the ds's. So lambda is going to be a constant, so if we were to integrate this, we would get the total charge along our arc length. All right, so let's go back here. dE is equal to k dq over r squared. Then we can write that as dq is going to be lambda ds divided by, let's just say, r squared. Now, if we'll look here, k is a constant, lambda is a constant. Is r a constant? Look at it carefully because, yeah, that r is a fixed value. It's a constant. So if I take dE, and I've not talked about the cosine component at all yet, so let's keep that in mind. We're going to have to plug that in. But if I integrate all of that, then I could factor out the k and the lambda and the r squared and just integrate over ds. So that's just the arc length. The integral ds, if I factor out lambda and I integrate ds, then this is just the arc length. That's the total arc length of whatever that happens to be right there. All right, so now let's include the cosine term. So I have to put in the cosine theta term and the cosine theta term there, and substitute in what we already know for this right here, that ds is equal to r d theta. So this becomes the integral, let's include the k lambda and over r squared times the cosine of theta, this is the integral, times ds, and ds is r d theta. Okay, this r, once again, is constant, so we can factor it out. We can put that right there, so that goes away. And you can see what's going to happen is that's going to cancel, and that just becomes a regular r, a 1r. Okay, let's continue on now. And you are about to see that this integral is going to get really easy. So the total e, which is the integral of all of the dE cosine theta terms, is equal to k lambda over r times the integral of cosine theta d theta. And now we have to plug in our limits, and that's going to be, remember, this only works if we're dealing with radians, so 120 degrees, that's plus or minus 60, so that's pi over 3 and minus pi over 3, like that. Now do the integral. That should be one that you can do in your head. That's going to be a sine, plug in the limits, and here's what you end up with. E is k lambda over r times the square root of 3. And there is our answer for the electric field at that point for a 120 degree arc. Well, let's put it in terms of total Q. Remember that total Q is the integral of all the dQs, which is that, and we can take that ds and plug in r d theta. So this is lambda r times the integral d theta from pi over 3 minus pi over 3. And when we do that integration there, here's what we end up with. I'll just write it here as well. Q equals lambda r integral d theta pi over 3 to minus pi over 3. When you plug that in and do the integration, you end up with lambda r 2 pi over 3. So if we take that lambda and solve for that, lambda is 3 total charge divided by 2 pi r. And now go and plug that in. E equals k lambda over, oops, didn't want to do that, sorry. E equals k, let's put that square root of 3 up there over r. And now this lambda becomes this, 3 big Q over 2 pi r. And I'm going to rearrange the terms here a little bit just to write E is equal to K, 3 square root of 3 over 2 pi r squared times big Q. There. Once again, electric field at the center of a 120 degree arc. Okay. And we did it for a negative charge, but you know, it really turns out it doesn't matter. If we did it for a positive charge, we would get the same equation. What would be different is the direction of the electric field. And in our case, if you'll think about that arc here, all these are negative charges. Here's that point. I'm going to have electric field pointing that way, 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 due to all of these individual charges along here. So what's going to happen is the vertical components are going to cancel each other out, and the horizontal components are going to add together. And that means that the net electric field, if I have an arc like this, the net electric field at that point points in that direction. So the direction for E is to the right as drawn. And that is our direction right there. So we've computed the electric field for a continuous charge distribution fairly easily. All right, let's move on and talk about a different charge distribution now. Let's say I have a ring of charge. So here's a ring. We're kind of looking at it from not face on, but sort of from the edge. So if this outer edge were the ring, we're looking at it like that, kind of obliquely. And let's say this is the center, and we'll draw a line out that way. And this has some thickness to it. So here's our plus charge on the ring. And the ring itself has some thickness to it that is very, very thin, but nevertheless it has some thickness to it there. We can shade that a little bit so it looks a little more three-dimensional. And it has a radius of big R. All right, and let's say out here at a distance from the center, let's call that distance Z. I want to know what the electric field is at that point right there. All right, well, I think using what you've learned so far, you can probably figure out what we're going to have to do. We're going to have to divide the ring up into little segments. If we integrated over this whole arc length, that would be the circumference of a circle, so 2 pi big R. But we have to divide it up into little segments, which we'll call ds segments. And within that ds segments, there is a charge dq. And since this is positive, that charge is going to create an electric field that points, let me make sure I get this accurately, points kind of downward in this direction. Whoops, so we'll draw that. That's our electric field component dE from that little charge segment at the top up there. And this distance from there down to there, that distance is square root of r squared plus z squared. Now z is a fixed value, big R is a fixed value. What we're going to have to do though is integrate around this whole circle here. So this hypotenuse as we go around the circle is also a fixed value. So this dE is going to be the same for components all the way around the circle. However, think about what's going to happen here. You're going to have components that are going to cancel. Now, is it the vertical components or the horizontal components that cancel for this one? Try to think it through before we go on here, and I think you'll see you can probably work this one by yourself at this point. All right, but let's continue on, and let's say that we define an angle, and this angle here is theta. That makes this angle back here theta. And theta is a fixed angle. Think about it. For every point along here, theta is not really going to change. It's going to go all the way around the circle, but theta stays the same. So we take theta and we can break this up into a component going this way and another component going that way. This is going to be the dE sine of theta components, and this is the dE cosine of theta component. All right, so for a component that's on the other side here, the opposite side of that, you're going to have it going up this way, and you will be able to break it up into components like that. So what's going to happen is these vertical components cancel like that. So really, the only integration we have to do is over this dE cosine theta component. All right, let's take that right there and run with it. So the total E is going to be the integral of all of the dE cosine of theta components, and the integral of the dE. Now let's think about what dE is going to be. dE is going to be K times Q. Okay, well, what's Q? If this is a charge distribution that is so thin that we can treat it like a line, then that's just going to be lambda times ds, where ds is that little section right there, and we're going to have to integrate around that whole circle, okay? Divided by r squared. Well, what's r squared? This is the distance. This is the distance away. So when we square that, we're left with r squared plus z squared times the cosine of theta. Now, the cosine of theta, this is theta, and remember it's a fixed value. Cosine of theta is going to be adjacent over hypotenuse. So it's going to be z over the square root of r squared plus z squared, like that. Look at this and let's see what are the limits of our integration going to be. We need to go around the whole circle, and we're integrating ds. So it's going to be from 0 to 2 pi big R. Let's factor out the constants. K is a constant, lambda is a constant. This everything on the bottom down here is a constant, so we're going to have an r squared plus z squared to the 3/2 power. This z on top is also a constant, so we can factor that out. So what are we left with? 0 to 2 pi r of ds. So when you integrate this, it's trivial. K lambda z 2 pi big R over r squared plus z squared, that's a squared, to the 3/2, like that. Okay, well, look at this. Lambda times 2 pi r. Remember, 2 pi r is the circumference. So if I take the linear charge distribution, multiply it by 2 pi r, that right there, that's the total charge. So this is K times Z times Q over R squared plus Z squared to the 3/2. So there you have the electric field for this distribution some distance Z away. Okay, let's check it, mentally perform a mental check. Let's say what happens if Z goes to 0. In other words, at the center of the disk. Now, at the center of the disk, you expect the electric field to be 0. And the reason you expect it to be 0 is not because of the magnitude, but because the directions of these electric field lines in the center of that flat circle there are all going to cancel each other. So you expect there to be no electric field as Z goes to 0. Does it? Well, I've got a Z on top and I've got a Z on bottom. As that goes to 0, the Z on bottom goes to 0, but we don't have to worry about dividing by 0 because we've still got this R. So as Z goes to 0, E goes to 0. That makes sense. So it does make sense. Well, what about if Z goes to infinity? Well, if Z gets very, very large, then this R squared by proportion becomes very small. So in that case, as z goes to infinity, z is much, much larger than r. So this z squared or r squared plus z squared terms just effectively becomes z squared. And if that's the case, then z squared with this becomes z cubed on bottom, and you've got that z, it cancels, so this becomes kq over, I should say, z squared. So as you get very, very far away, z becomes very large compared to r, then this becomes more and more like a point charge, and that's the equation for the electric field of a point charge. So that's exactly what you expect if you were to get very far away. Okay, I've probably done enough damage for today. Let's go ahead and quit here, and we'll talk about something else next time.